In this video, we are going to find real numbers x and y such that x equals y times 3 minus y all squared and y equals x times 3 minus x all squared. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. We notice that if x equals y, there will be many obvious solutions. Say, for the first equation, we can deduce that x equals x times 3 minus x all squared, and if we move everything to one side, we have x times 3 minus x all squared minus 1 equals 0. So we have x times x squared minus 6x plus 8 equals 0. So we have x equals to either 0 or 2 or 4. Of course, y have to take the same value. So we have three better solutions very quickly. Now what happens if x is not equal to y? Then we subtract the two equations, and we have x minus y at the left, while for the right we have y times 3 minus y all squared minus x times 3 minus x all squared. Expanding, we have 9 minus 6y plus y squared and 9 minus 6x plus 6 squared in the brackets. So gathering the terms with common factors, say 9y and 9x, then we can take out the common factor 9, and then for the y squared and the x squared, we have 6 times x squared minus y squared, and finally we have y cubed minus x cubed for the cube terms. So then for all terms have a common factor of x minus y, so I'm going to review the common factor minus this product, and so now we can divide both sides by x minus y because we have assumed that x is not equal to y, so that means x minus y must be non-zero. So then we have 10 equals 6 times x plus y minus x squared plus xy plus y squared. Now at this point, it seems our equation depends on x plus y over here, and for the quadratic expression, I can rewrite that as x plus y all squared minus xy. So I'll say it's also in terms of xy, sums and products of the two unknowns that we have to solve. To make things look easier, I will say let p equals x plus y and q equals xy. Then I can say that 10 equals to 6p minus p squared plus q. Now on the other hand, I'm going to make use of the symmetry of the system in another way. I'm going to multiply the two equations. So going up, we have xy at the left and xy times 3 minus y all squared and 3 minus x all squared. So there are common terms at both sides, which is xy. So either xy equals 0 or the product of the squares is equal to 1. But for xy equals 0, we've actually done that already. That means x is 0 or y is 0, but if 1 is 0, then the other has to be 0 as. So that means I can just replace this OR with AND instead, and we've got the solution already. And for the other part, we have 3 minus x times 3 minus y to be 1 or minus 1. Now we can also rewrite these equations in terms of P and Q. xy expanding, as I can say, xy minus 3 times x plus y plus 9 is equal to 1 or minus 1. So either it's a plus 8 equals 0, or similar things, but not plus 8, but it's plus 10 equals 0. So that means q minus 3p plus 8 equals 0, or q minus 3p plus 10 equals 0. And then we have to deal with these three equations and try to solve for p and q, and hence x and y. Now from the equations at the bottom, say I'll write this as equation 1, equation 2. Now from 1, I can say q equals 3p minus 8. And so I'll put this I'll call this equation star, so I can write less. I will have 10 equals 6p minus p squared plus 3p minus 8. And so eventually I will have p squared minus 9p plus 18 equals 0. I can solve it, and I have p equal to 3 or 6. And consequently, q equals to either 1 or 10. And for each case, we've actually established a system for x and y. So either the sum equals to 3 and then product equals to 1, or the sum equals to 6 or the product equals to 10. Then I can say x, y are roots to either z squared minus 3z plus 1 equals 0, using the concept of sum and product of roots, or z squared minus 6z plus 10 equals 0. So for the first case, I will have 3 plus or minus root 5 over 2, while for the second case, I will have 6 plus or minus square root of minus 4 over 2. So I have to reject this because I'm looking for real numbers. So from the former case, we have xy to be either the plus root 5 one for x, or the minus 1 for x. And y will take the other. So that's the first case when we try to solve for p and q. Now it comes to the other case, which is q minus 3p plus 10 equals 0. But I'm going to just say that using a similar argument, then 10 equals 6p minus p squared plus 3p minus 10. So p squared minus 9p plus 20 equals 0. So p is either 4 or 5. And q is equal to 3p minus 10. So for the 4 case, it should be 2. While for the 5 case, it should be 5. Then similar argument again. I'm going to solve for the quadratic equations z squared minus 4z plus 2 equals 0, while for the other one we have z squared minus 5z plus 5 equals 0. So x and y are either four plus or minus root 8 over 2, while y has to take the other. Then of course I can simplify, which gives 2 plus or minus root 2, and then y will take the other, 2 minus or plus root 2. That's the case when p and q are equal to 4 and 2 respectively. As for the other case, if it's 5 and 5, then we have 5 plus or minus root 5 over 2, and again y will take the other. So altogether there are quite a lot of solutions. We have this pair, or actually I should say two pairs, the third and the fourth pair over here, fifth and the sixth pair over here. Of course, we can also say the first three pairs over here, xy equal to both 0, both 2, or both 4 are also valid solutions. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.